think we're ready to begin. Don't want to keep the people who came first waiting. So welcome to the MicroLED Association Yield webinar of MicroLED Yield. This is an open webinar that is based on a recent white paper that I have to ask some people to mute. Yeah, so let's begin. Welcome to the MicroLED Association Yield webinar. So this is an open webinar that is based on a recent white paper that the association published in early February. You are all welcome to download this white paper from our website. And in this presentation, we'll first explain what are yields and why yields are so important in the display industry, and how MicroLED production differs from other kinds of production processes, like for LCDs and OLEDs. We'll then talk about the specific yields and specific challenges in MicroLED production. And in the final section, we'll present some strategies to overcome the yield challenge, as we call it, and solutions by some of our members. And we have some noise, so we'll have to mute everybody. And if anyone wants to unmute, please let me know. You can use the chat. Okay, so what are yields? Basically, yields is pretty simple. It's the percentage of panels that are usable from out of all the total panels that the production process goes through. Other panels are defective and has to be repaired if possible or discarded. So getting good yields is extremely important. The display industry is very competitive and there's a huge pressure to reduce costs. If you throw away some of your panels, you lose a lot of money, obviously, and this is quite straightforward. And current display technologies, LCDs and OLEDs, have matured, and production yields are very high. In most cases, over 90%, even higher. And even when introducing new technologies, it's possible to achieve very high yields and very quickly. For example, we give here an example of Samsung display with the QD OLED panels, and they manage to increase the yields from around 30%, 20-30% to over 80% in less than a year. This is impressive, and this is a new kind of technology. So it was very indicative of the status of, the matureness of an OLED production process. LCD is obviously even more mature. And we have to remember that this is the kind of matureness that, that MicroLEDs will have to compete with. So one thing I want to discuss is how size affects yields. And before we start discussing MicroLEDs. So the larger your panel, basically, the lower your yield. And I give an example here. Let's say we have a big substrate with 2 defective pixels. You can see them in red here. If I have 24 panels on this substrate, let's say this is smartphones, then I will have 2 defective panels, and that's 2 out of 24. So my yield is 91%, because 22 of these panels are okay. Sorry. Yeah. If, however, I make 3 TVs on the same substrate, then two of these TVs are defective. So my yields drops to 33%. Only one is, usable. So I think this explains why size is so important, and we're going to talk about this later. So now let's take a look at how MicroLEDs are being produced or will be produced. Unlike LCDs and OLEDs, where everything is produced on a single substrate in one process, with MicroLEDs, we have a different kind of thing. We have 2 production tracks. The first involves the production of the LEDs. You see it on top here. And the first is the LEDs, and the second is the backplane. The LEDs are then transferred to the backplane in what we call the transfer process, or the pick and place process sometimes. And then everything is combined. And this means that unlike with OLED and LCDs, with MicroLEDs, we actually can talk about 2 different kinds of yields: the LED production yield and the transfer process yield. We kind of disregard the backplane production yield. This is a mature process, and it seems as if the MicroLED industry is going to use the same kind of backplanes as LCDs and OLEDs, this hopefully. So this is going to be a bit out of scope. Now, if you look at high-end TVs today, we have 4K resolutions. at least 4K, and this is over 8 million pixels. And with micro-LEDs, this means that we have over 24 million subpixels or individual LEDs. So unless we dramatically increase the production yields for LEDs, it's going to be very hard to achieve high yields for LED production, even at 99.99999, that's 5 nines. Even at this kind of yields, we're going to have an average of 2 LEDs that are still going to be defective in each panel. And obviously, these numbers are just numbers, but it's important to understand that with micro-LED, we are not seeing a future where the yields are going to get to 100%. And this is true for both the LED production process and the transfer process. And as we're not reaching 100% yields, we're going to have to rely on inspection and repair or using redundancy or some other techniques to solve the problem. And it's important to note that it's not just about defective LEDs. Some smaller defects may result in operative LEDs, ones that can still be used, but do not output the light in the way that we want. There could be a variation of color or brightness, and this could affect the display quality as a whole. Displays can be non-uniform, can have mirror effects, and this is something we definitely want to, avoid. And the last thing I want to mention is that when I talked about the pick and place transfer process before, and that's what I would call the classic kind of process, the one that takes LEDs from the wafer and places them on the display substrate. It can be with or without an intermediate donor substrate stage, but it's important to know that we have several alternatives to this process. For example, sometimes LEDs can be grown on the substrate or a completely monolithic process, what is called. And this is a bit out of scope of this presentation. So we assume that we're going to have LEDs transferred, and so we're going to have to look at LEDs yields and transfer yields. And towards the end, when we discuss specific technologies, then we're going to see some alternatives to that. So let's start. The first critical junction in LED production is the LED production, what we call the AP wafer stage. And growing an LED stack on a wafer is never done with perfect condition. So some areas on the wafers may turn out defective, and as we said, some parts of the wafer may be okay, they could work, but would not be optimal. And then we have the chip processing stage. There's a second stage that singulates the LEDs and turn them into devices that we can work with, and this also can destroy some of the chips or the LEDs. It's important to note that these are very, very small LEDs, micro LEDs, sometimes 1 or 2 microns in size. And even a small defect can affect a lot of different LEDs that are close together on the wafer. And this could have problem in many transfer processes, LEDs are moved together, and so a complete area of the display could be affected. So this could have gross repercussions where we compare this to a single LED that's maybe not effective but not operating optimally, and we'll discuss this later on. So LEDs makers apply inspection technology. That's how we do it today. So we find defective and non-optimal areas and even individual LEDs. So when we have classic LED production, we inspect and tag the LEDs and bin them. And so it's possible to sort them by performance. It's called binning, and then this can be used. For example, if you make lighting, you can choose some LEDs that are not optimal, but this will be used maybe for lower cost, application. But in micro-LED display production, this is not really useful because the display performance has to be pretty uniform, and even one bad LED in a display is not something that consumers will agree on, especially as these are high-end and premium displays. So some of these bad LEDs can be repaired at this stage, and this is something that's definitely on the table. And it's important to note here again that low yields have a dramatic effect on the final display cost. In micro-LED production, it seems as if the cost of the LED chips themselves is going to be one of the largest cost drivers in producing the entire display. And if you have a lot of defective LEDs, that's going to increase your cost beyond making the transfer process a challenge. It's important to note also that the integration between the epi wafer stage and the transfer process stage is and could be a very big challenge. And it could be the key to successful display production. So some transfer processes are more flexible in how they take and pick in the LEDs and how good LEDs are going to be used, while LEDs can be discarded. Again, we'll discuss this later on in the transfer process and towards the end of the presentation. So after we finish the LED wafer, we're looking into the transfer process. This is another critical stage in the production. And again, it could harm the LEDs. This is especially problematic in mechanical transfer processes when you have a stamp that picks the LEDs from the wafer and, using mechanical force. And another failure point can be the placement and the bonding of the LEDs. This has to be extremely precise. You have to have very good alignment. Otherwise, again, you're going to have defective areas or single LEDs. So all of these transfer processes that I mentioned here, everything is quite new. The industry is still at a very early stage, and none of these technologies are actually mature. And we are seeing that the move from the lab kind of very early pilot production to actual commercial processes is a big challenge, and this could take years to solve. And it could be that the industry will face very bad yields for a long time in the transfer process. So I think by now we understand that we're going to have defective and non-optimal LEDs on the source wafer, and also the transfer process may harm these LEDs. So we're going to have, even if we repair them on the wafer or choose not to pick them, we're going to end up with bad LEDs on the final display substrate. So display makers, looking at it from the display maker point of view, they have two kind of strategies to overcome this issue. So first of all, we should always strive to maximize your yields. If you work towards cleaner LED production or minimizing defects and problems using the right materials or innovative technologies, and also connect the transfer process with the epi wafer process in an optimal way, you're going to have increased yields and a better situation. And this can improve everything, but it's not going to solve the issue. That's highly unlikely, at least in the foreseeable future, to have 100% yields. And so, as we said, consumers will not agree to have any defective LEDs or problematic displays. So display makers have to rely on some kind of mitigation strategy. We are seeing a lot of effort going into inspection and repair processes. And there's also talk about LED redundancy. Both of these technologies are early stage because we are talking about doing the inspection and repair in line with the production process. We will have to have very effective repair processes, and redundancy could be, a solution, but it also brings a lot of problems, especially in cost, because we're going to have, as we said, LEDs, expensive LEDs that we're going to have to make much more of them to solve this. So I think by now we finished the overview of micro-LED production and yield issues. And now we want to take a few of the latest technologies being offered by MicroLED Association members that help to solve this issue. So we're going to do this alphabetically. The first one is 3D Micromac. This is a Germany-based laser micro-machining company. They offer innovative laser solutions for mass production of micro-LEDs based on UV laser technology. So they have solutions basically for three kinds of processes. And this is interesting because we are starting to look at specific processes here. So the first one is LLO, or laser lift-off. That's actually the second one on my list, but I want to talk about it first. And here a laser is used to remove LEDs from the original wafer, from the epi wafer, into a donor film, usually. The second process is lift, or laser-induced forward transfer. And in this process, we transfer the LEDs from the donor film to the final substrate. So these are similar processes, but they also have their differences. And 3D Micromac offers tools for research and production in both LLO and lift. And the advantage of using lasers here is that we do not use mechanical force. And as we said before, this is one of the big pain points in transfer processes. And so this can affect the yields and improve them compared to other processes. 3D MicroMark also offers repair and trimming tools based, again, on their lasers. And these systems can target a single LED die and can be implemented in every step of the production process. And this is important because, as we said, we have a lot of failure points, and it depends on your architecture or process architecture, whether you want to fix things along the way or wait till the display is produced and then fix everything. And 3D MicroMark offers solutions using lasers for each of these processes. My second company is ASMPT. That's a multinational equipment maker based in Singapore. They offer several systems and technologies for microLED production, including mass transfer, mass bonding. They're working with many producers. And here we wanted to focus on a specific technology, and they call it active tilting control. Now, as you can see here below, when you have a stem-based peaking tool, it's very important to make sure that the head and the substrate are completely coplanar. So otherwise, the LEDs are not picked up correctly or even damaged if it touches the wafer. So it's quite common to use passive tilting control that's shown here on the right, but active tilting is reportedly superior as it does not damage the peak tool if the tilt is done too close to the wafer. As you can see here in the image, that's a superior process from ASMPT. The next company is CA-Leti. This is a research institute in France. They have been active with micro-LED R&D for many years. And here the researchers advocate for a long time a unique approach to combine micro-LEDs and micro ICs to create what they call a smart pixel, which is a small display engine that includes a CMOS micro IC, the controller, and the LEDs on top of it. So each of these individual pixels are then, can be moved to the final display backplane. And one of the advantages here is that the backplane is relatively simpler, compared to an active matrix one. And a major advantage here is that it's easier to inspect these smart pixels. You can use contactless EL mapping, for example, and then you can transfer using a selective transfer tool. You can choose to select only the workable display engine. And according to work done at CEA, it seems that simplified testing results in actually improved yields. And we see several companies offer similar architectures for micro ICs. Next up, we have Coherent. These guys probably don't have to introduce them, a world leader in laser components. They've been a long-time supplier to the display industry, and they offer lasers and solutions in several potential processes. These include LLO and lift, which we talked about before. There's the ELA process, which creates the LTPS from amorphous silicon. They're using lasers to repair the LEDs and more. And we wanted to focus here about, they are driving towards mature processes and durable and efficient ones. And one of the unique advantages of the shortwave UV lasers that Coherent is developing is that they have a very large pulse energy. So this can be actually multiplexed or split using a photomask, which you can see here below. And so you can work on hundreds or even more of LEDs at the same time. So this not only increases the productivity, it also increases the yields because of the uniformity of the process. The next company is Comptech, based in Finland. It's an early stage company. They developed a unique approach to protect materials using ALD passivation. The technology protects the sides of the LED. And as you know, the sidewall defects on micro LEDs, that's one of the main reasons for failures and reduced efficiency in LED production. And the main driver to protect these LEDs is to improve the efficiency. But they also found that this also reduces LED defect and improve the wafer uniformity. So this could be quite useful again to combat bad yields. The next company is Elax, a US-based company, and they developed a unique and I think an interesting transfer process. Basically, they call it a fluidic process, which means that the LEDs are removed from the wafer and dissolved in a special ink, which is then spread over the substrate that has special holes. They call them wells, and the LEDs actually self-assembly as they fall into place. This is a unique process with many advantages, and one of the advantages is the high yields. So the main reason here is that you can tune the process so bad LEDs or defective LEDs and are not picked up by the process into the ink and do not fall into the well. And this means that only working LEDs are actually used. And this obviously affects your yields and improves it. But a main advantage here is that this process actually randomizes the LEDs. So you take the LEDs from the wafer and put them into the ink, and they all mix together. And then two LEDs that were next to each other on the wafer do not end up next to each other on the final substrate. And again, as we talked before, if we have an area on the wafer that includes several, not defective LEDs, but LEDs with slightly less, slightly better performance, if we group them together, this is visible and problematic. But if you spread them out randomly, this could be actually usable and not detectable by anyone seeing the display. So this has a nice effect on the yield. Next company is Israel-based Inziv. They developed a unique inspection tool specifically tailored for microLED production. And the tool combines PL, EL, and nano-optical measurement. That's three different tools in the same platform. And the basic idea is that it's possible to use very fast PL to quickly identify problematic areas on your wafer, and then use the more precise tools, the EL and the optical measurement tool, for individual LED production. And the company adopts and uses special AI technology, which greatly reduces the time needed to inspect complete wafers. And again, as we talked, inspection, especially as combined with repair, going to have dramatic effects on your production process. Next company is Custom Dot, another early stage company. They develop quantum dots, especially for the microLED industry. That's cadmium-free nanomaterials, and the idea here, obviously, to adopt them for color conversion for microLEDs. And the company, as they explained in our white paper, the microLED architecture that uses, the basic structure uses blue LEDs with color conversion layers, and this can actually increases yields. And we can look at two alternatives. First one is, as you transfer the blue LEDs from the wafer to the display substrates, and then you deposit the QDs on the display substrates. And the main advantage here is that you have a simpler transfer process because you're only handling blue LEDs. So the transfer process takes LEDs from a single wafer, all of them, blue LEDs, and it's easier to optimize the process for a single LED type. The other possibility is to deposit the QDs on the wafer, when they are still on the AP wafer. So you take the blue wafer, you deposit the LEDs, and then you have red, green, and blue LEDs or devices on the wafer. So again, now you have to transfer them to the display substrate, but unlike in a regular RGB display, you're still using a single wafer. So you take three different kinds of LEDs from the same wafer, which still have advantages compared to an RGB, a classic RGB process. So this is obviously one thing to consider when you look at your architecture, whether using color conversion or RGB, regardless of the other advantages and disadvantages. Next company is Radiant, a subsidiary of Konica Minolta. That's another company that develops inspection systems. They have customized and automated systems. And again, we're talking a lot about inspection here, and that's one of the most important issues and key aspects of these processes. So for microLED, Radiant developed a system that combines its own patented software and hardware. So there are two sides here. First of all, you quickly analyze and detect the LEDs. You find defects and bad performing LEDs. And then they have a software that can use a computer and software to actually correct the factors or look at the factors that need to be corrected at the panel level. So this is something that can be implemented following production to fix problems such as MUA. You can see the example here on the left. We have the original image, on the right, how it looks like after correction. And this is something, again, a sort of strategy you can use to fix some of the problems on your final display. Another interesting technology from US-based company, Terrace Circuits, and these guys developed a transfer process, or actually a material that adopts to a process that's based on their own material that was specifically engineered to support this kind of process, the leaf process. We talked about this before, the laser removal process. So the leaves transfer LEDs from the donor film to the final substrates. That's the end of the process, of your transfer process. And the idea about the Terrace Circuit material is that this is a material that's sensitive to UV light, and as you shine light on it, it releases the LEDs, drops them because the material dissolves. So using the technology, you can use a patterned mask. So use the mask between the material and your UV source. So you control which LEDs are released and which one remains on the donor film. And you can actually customize these LED masks on the go. So you can actually use a mask to remove all the, for example, one idea is you can take the mask, find out which one of your LEDs is defective, create a special mask to remove these defective LEDs, and then all the LEDs on your wafer are then usable. You can obviously use, you can use then a complete mask. You can actually use a mask tailored to move just the working LEDs. That depends on the kind of optimization you want. But anyway, this is really useful to solve the LED problem, the yield problem, sorry, in LED, transfer processes. And the final company we have is ViewReal from Canada. They, another early stage company, they developed, a complete process actually that takes, from the AP wafer stage to the final production. And the basic idea is that they can remove LEDs from the AP wafer and place them into what they call a cartridge, which is sort of in between, a holding mechanism for these LEDs. And then the LEDs in the cartridge are printed onto the final display substrates. This kind of technology has a lot of advantages. One of them is that it is possible to inspect and remove LEDs from the cartridge. So this basically means that you can, following your LED production process, you can move everything to this cartridge, inspect it, and remove it quite easily. And then your printing process, in this case, the printing process actually starts with 100% working LEDs. And obviously, this is great for the yield process under these conditions. So that's the ViewReal technology. And this concludes our talk today. I hope this was useful. Like I said, I hope this explained quite a bit about yields, or at least give you some taste of what are the challenges and what are the kind of solutions that we are seeing in development or actually in production and commercialized now. Like I said, this was based on a white paper we recently released. This has a lot of more information. You are free to download it, from our website. You can click here in the MicroLED-Association.com. And the MicroLED Association, I'm going to give a short introduction. It was established last year to help companies in our industry to collaborate, to share information, and to promote MicroLED technologies and their own solutions in the market. Then we established it in August 2022. We have grown to over 30 companies. We have industry leaders, startups, we have suppliers and researchers in universities. And we believe that our work here, as we grow, will become more and more important to actually educate the industry and outside of the industry, and also help foster collaboration here in our industry. And that's part of the reason why we hosted today's lecture. So you can see more about the association in our website, and you can feel free to email me in the address you see here. We always welcome new members. And thank you. I hope you enjoyed this presentation. I'm now opening it up for questions. So let me stop the share, and then if anyone have any questions, you can unmute or raise your hands and you can ask them.
Hi, here is Alam from Extron, Germany. My question is, what is your idea? Which method would be at the end the winner, and which one is the most effective and with low cost and fast method? Too many questions.
That's a big question. Yeah.
I pay money for the right answer.
I should be careful here. So I'm going to give a diplomatic answer, but I think that's also the correct one. First of all, it's way too early to know. We are seeing a lot of, established technologies like stamping and lasers that are being adopted today into production, and we are also seeing, early next generation technologies from, different kind of companies. I would say that first of all, it's too early to tell, and second, a lot would depend on the application. So I think, in LCD and OLED production, we got used to the fact that pretty much all the producers use the same technology and use the same architecture, maybe with small variations, but the processes are pretty much the same. According to what we believe, the microLED production industry, if it reaches its potential, it will probably have very different kind of processes. And we even see it today. So, if you make micro displays for AR, very small displays, you're going to use produce them on silicon wafers or use silicon wafers as substrate. And then the production process looks very different than what we're going to have for large area TVs or IT displays. And it's very likely the different makers will actually adopt different technologies here. So we don't see something specific that will be used across the industry, but, you never know. And Alexander, you want to?
Thank you very much.
I just wanted to show my face. Hi, everybody. Thank you very much, Ron. I think a really good introduction. Introduction, I think, to rumble everybody's interest here and have a discussion about what actually is the opinion of the audience in a way to the colleague of Extron. And what do we believe as an association, as the members and the other people joining, how we can address this? And for me, I want to, in a way, tease everybody. What do we believe? Do we believe that it will be more relevant to manage the damage which is occurring during the process and the cost associated with that? Because in the end, it's all about cost, right? You have many ways of sorting, binning, getting the known good die onto the backplane in whatever method. But in the end, it's about cost, right? The throughput and the cost you can do. And the other is in a way, how much can we spend on the materials to start with to avoid this cost? Yeah. So to give you a very bland example, and of course I'm biased here, we make gallium nitride on silicon wafers, 203 millimeter diameter, to process them in silicon lines for high yield. So I'm completely biased, but so the hypothesis is, if you make the wafers 3 times as expensive, the wafer from which the micro-LED chips are made, is this then helping you to overcome the cost later on? If that wafer is in a way perfect, right? That you get the, I think it was 7.9 yield you assumed at the beginning, right? Where we would have 2 failed pixels. So I think that's something which I'm really interested in to kick the tires here a little bit and see what the opinions are.
So anyone who wants to join, feel free. I would say that, again, this, I think, simply even shows in more clearly that you're going to have different options as a producer, right? So you're going to say, I'm going to start with a very good AP process or buy very good, LEDs, and then I'm going to use a different kind of process at the end to transfer because my LEDs are very good. Or I'm going to invest more in, repair or inspection. And like you said, I think one of the key issues is going to be time, right? So if you're going to spend a lot of time, like what we see today, that some repair processes could take several days to completely inspect and repair, a single TV, and that's obviously not, not something you can rely on for mass production. So, it's a good question. It's going to be all about the cost, and then I think it's too early to know today, but these things will start to get clearer as, production moves forward, especially as we see display makers bringing displays now into the market. I see one of the the chat, I've got a chat question about Samsung. They showed 50-inch micro LEDs, right? And we don't know the complete specification there or the production process, but these guys are obviously targeting, residential kind of premium TV production, and they're going to have to reach pretty low production cost to make this feasible. And that's actually going to be the topic of our next white paper about TVs. But these are all good questions, but I think it's just too early to tell, right? So, and I hope for the industry segment, we're going to see a lot of different solutions being adopted by different makers. I think that will enable it to actually process. Yes, hello, David. Hey.
Hi. So, just to jump off Agdan's question, I think it's just a question of test or repair. I'm going to say something which might work against my own technology, but it's less about test and repair, but overall cost per wafer. So, let's say if the wafer costs, I think, if you look at the production of a fab, there's going to be something like 5 to 10% or 20%, let's say, investment in test and repair. And I think that, that's going to come up into one package. And I think I do tend to, so I think it's going to come down to the overall cost, and that's, as you said, going to come down to overall time. It's the cost going to vary, but it's going to be price per wafer at the end of the day, or price per chip, whatever way you look at it, which we think, which I think is going to be the determining factor. One thing which, I want to just throw into the mix over here, we're putting a lot of, and it's something we're going to be announcing soon, we're putting a lot of effort into a fast EL process on the chip level to do very large EL inspection at the wafer level before the transfer, similar to the direction which Alexander was saying of ensuring that what's being transferred, that the quality is at a high level, so that you're transferring only the good ones ahead of time. And we believe that should help move the process along. But of course, that's my own little information here. So I just wanted to add that to the picture.
Thanks. Yeah, I think it's going to be interesting, especially as some companies are talking about decoupling the process, right? So actually buying LEDs from AP wafer LEDs, and then will you buy them already inspected? Will you buy them, with kind of software information, which one is okay? Will you buy them repaired already, or will you do this in-house?
Right. Right now, we're seeing that, both sides are interested in doing their own testing and inspection, but I assume that's partially because of the low quality. And as that improves, one side will be the winner. And I can tell you my guess, but I'm not going to do that in this forum.
Maybe later. Yeah.
I'm curious. Maybe we need to make some assumptions and express them in dollars or euros, whatever most people feel most comfortable with. If we make an assumption about such a large television, how much can the pure LED chip cost be? Because I think, Ron, you pointed that out quite vividly, if I got you right, that in the end it's the yield of the chip, right? How many of these chips are actually yielding, which you put onto the display? And I hear a lot of the transfer people telling us they have next to 100% yield, whether that means 98 or 99.99999 something. But if we assume for a moment that yield is really like 99.59 or something, so the 79 which you highlighted, what does it mean? How much can this cost be? Is that part of the next white paper, or is that something where we can make some assumptions based on the amount of chips and the size of chips which go into these displays? Because then we could compute how much actually a wafer could cost to make affordable televisions.
So, in our previous white paper, we discussed the MicroLED for wearables, and then we had a good cost. I think a good cost discussion. It was also easier because wearables have very small resolution, so we're talking about hundreds of thousands of LEDs and not tens of millions. And yeah, so we are still working on this white paper about TVs, but I think this cost analysis should be part of this white paper. I mean, it is, and we're going to discuss this because, yeah, it's going to be important to see what kind of LEDs you're going to make, what's going to be the price, and how much should you invest in inspection and repair, or bringing out the LEDs in the first place. And I think this also starting to get into the question of what size of wafers you're using, right? I mean, when you're talking of tens of millions of displays, it's going to be much more economically, but better economically to use larger wafers if you can make them, with good enough quality, and then the cost per chips drops dramatically. And I know I see you smiling, Alexander, because that's why you asked me.
Yes, as I said, I'm really biased, so I don't want to. I see that there's other people unmuting, so I want to keep shut for a moment.
So maybe also, yeah, here's Oliver. So I think
there.
this is the main question, and we are still at an early stage. So when you look back for let's say we are also having a lot of OLED equipment, and if you go to a fab today, I think it's from the first tool to the display, everything is known, and there's one process chain. All fabs are more or less the same. And if you see how today everybody wants to have a piece of the cake, and for each individual process steps, it's quite early. But I think if we start with one wafer, so we know that for a 4K TV, large TV, we need about 24 million micro LEDs. So the question is also the size on your EPI wafers. So can you, what I'm always explaining to customers, one wafer per TV, 24 million, or can you go to 240 million? So you can make already, then the costs are tens. But if you get smaller EQE, and so I think there are so many different let's say parts that play the role of the cost, and starting with EPI wafer, so not with the processes and yield and everything.
Yeah, I completely agree, and I don't want to argue that the EPI wafer is in a way the only thing you need. But
No.
but my thinking was more, maybe we can make some assumptions. Yeah, for example, we go for a 4K display, so it's the 25 million, 24 million odd chips, and then we assume a certain brightness level we need per area, to compete with OLED, and surpass it, of course. And then from that we know how bright the chips need to be. Yeah, and then we can make certain assumptions how big a chip needs to be to emit that level of light. And then we know basically how many chips we get out of wafer. So just to give you an example, out of an 8-inch wafer, if we have chips which are 5 by 5 micrometer, which is what some of our customers are targeting also for the larger area displays,
yes,
we are getting more than 600 million chips from a single 8-inch wafer. So if that goes up to 12-inch, 300 millimeter, we are talking about 1.5 billion chips on a single wafer.
Yeah.
And I mean, if then the 5 by 5 micrometer chip size is not sufficient, well, then this is not working. But if that is an assumption, if we make it 10 by 10, then we just need to divide by 4 roughly, and then we can make assumption. Okay, how much is actually the TV able to afford to spend on this? Because there's the backplane, some whatever glass sheet on top. I don't know. I'm unfortunately not completely into this. And then if we have that per area cost basically for the display, we can then compute what the wafer can cost. And the wafer then will break down, okay, how much can we afford for transfer, for testing, for processing, and for EPI? And then we can get an idea of where is the money more wisely spent. Because if it, for example, if it's costing twice as much to make an EPI wafer, which gives you 1 bin wavelengths, as our wafers can do, but if that is twice as expensive and it does not pay, well, then let's forget about this plan and just go for 2 bin EPI wafers and do the sorting and binning. And that's kind of something where I wanted to.
Yeah, I think it's all together. So I think also Ron, for you, to have these roadmaps. So we all know and we all hear 5 micron is the goal. Some are far or more far away, and some are more close to this. So also, as we said, with our technology, we can handle 5 micron. Other technologies can handle maybe 20 microns. So if you change to a different whatever transfer step, maybe you have to change your technology again. So that's what I mean. The same is for EQE. People are working on getting higher or better micro LEDs at a 5 micron level. And I think that's like everybody is working on his homework, and everything is getting better every day. And yeah, so the question is which are the big parts, or where are the cost roadblockers or whatever to what must be solved most or first to get this done.
And yeah, and I agree with you, Oliver. It's basically it's too early to know. I mean, in today, today TVs, when you look at the Samsung and the Sony, there are LG also, they're using tile displays. They're using smaller modules, and then you have another kind of variable in your equation, right? So suddenly you're talking about yields for a smaller module and not a complete display. So how much money and effort will you put into better LEDs and better transfer? If you're making smaller modules, maybe you can throw away 1% of these modules, and still it could be more effective than investing a lot of money in your other processes. But then obviously you're going to have to make tiled, the technology to make tile displays much cheaper than today. So, I would say too many variables today still. Yet.
Yeah, even if you see now, we are talking about 24 million so RGB. So now we see a lot of effort in making a single chip RGB. Then you don't need 3 times anymore. So this is already affecting the yield if you just have, let's say, the one chip and not 3 colors, single LEDs. Yeah, and yeah, again, there are so many influences today, yeah. And yeah, let's see.
Yeah, it's going to be interesting, that's for sure.
I have, hello, I've done a bunch of modeling on OLED versus micro LED, and I'll give you some numbers and you can kind of deal with it. If you looked at a 4K OLED, say in 2025, the material cost, that is the material and putting it down, it's going to cost about $50. And if you look at the depreciation, that is the deposition tools and the thin film encapsulation, that's going to cost about $100. Everything else is going to be about the same. So you have about $150 to be comparable on 4K. With 8K, it doesn't really grow that much for OLEDs because it's pretty much the same amount of OLED material and the same deposition tools. So obviously the higher the resolution, the more expensive it is for micro LEDs. But I think those are the critical numbers that you have to target. That is being able to grow the LEDs, being able to bin them, being able to fix them if they fail. You can't have in a TV, you can't have a single point of failure. I mean, that's just not. We learned that when we started to show video on LCD screens. We used to have 3 or 4 pixels failures acceptable, but as soon as video came out, it became 0. So that's the way the TV market is right now. So those are kind of some of the numbers. I don't see much difference in terms of personnel, module, glass, encapsulation between an OLED or an LCD and a micro LED. So for a direct view display. So those are I think the critical numbers that you have to deal with.
Thank you, Barry. Hello. So first of all, I think this demonstrates what kind of competition with micro LEDs are going to have. And, we are all advocating micro LEDs, or the association and members, we are advocating micro LEDs, but we have to remember that the fight against OLEDs and LCD is going to be an uphill battle in terms of cost and performance. And, I think even if we are very optimistic today, getting to these levels for 55-inch 4K TVs, it's very unrealistic for micro-LED. So first of all, we're going to start with different kind of technologies, right? So very large TVs. If you're making a 90-inch 4K TV or even 8K, the cost for OLED production, they grow exponentially larger. But for micro-LEDs, the cost of the LEDs can be pretty much the same. And that's, these are the areas where we'll see micro-LED starting, the fight against OLED TVs, and it's going to be a long one, I think. And that's one of the main reasons we don't see mass adoption in the next, 2 or 3 or 5, maybe even 5 years for these kind of applications. But that's it.
Ron, sorry, did I understand you correctly that you said that for a 8K display, the cost for an OLED is much higher than for 4K?
No, not the 8K, but the size. Like if we're talking about an 80-inch or a 90-inch.
Okay, yeah, understood. Okay, makes sense. Yeah, because I understood very differently, and I with the size, it makes sense. Yeah.
Probably I wasn't clear, but yeah, that's
now if we use this as a benchmark, and Barry, can you say for which display size you mentioned the $150?
That's 55-inch, I think.
That was a 65-inch.
Okay, and so does anybody know how much cost we would have for the backplane and whatever front glass we would have and the driver and stuff we need for a micro LED display, so we can narrow it down to what the chip cost may be?
Sure. The module itself, which would really be just the drivers and the power supplies, about $25. The glass, about $8 to $10. And the array material, about $8.
So the array material, Barry, is most of what we have to consider for the micro LED, which is comparable, right?
Oh, no. That's just for the active matrix for the display itself.
The backplane.
Yeah, the backplane.
So we're talking about something like $40 to $50 to make everything except the front plane in such a TV, in a 65-inch. Yeah.
And don't forget, there's a lot of kind of overhead that you have to deal with, like SG&A and indirect expenses the combination tends to be at about, for a display company, about 20% of the total display.
Yeah, I think it's just, taking these numbers just clear that we have a long way till you can actually consider making a 65-inch
or
that's competing in cost with OLEDs.
Yeah. The other question I would raise, if anybody has any answers to, is studies that I've been doing looking at power consumption, and that's the efficiency of a 5 micron by 5 micron LED. And even at the blue, I wonder how it competes with OLEDs in terms of efficacy.
So we actually ran a couple of articles on micro-LED efficiency about a year ago, and I think there were 2 main conclusions. Is that first of all, with most displays, most of the power consumption is not lost in the front plane. It's actually lost in the back plane, and all kind of filters and things you add on top, and then something like 30-40% is actually what you can account for the front plane, and then your overall power consumption efficiency is limited by this number. And you're totally right that when you go to these kind of sizes, you have a severe efficiency drop in most micro-LED technologies. And again, it's a bit early, but we have some technologies that aim to fix that. We talked about Comtech, for example, from Finland. They are using passivation to actually fight the drop in EQE as you lower the micro-LED size. We're talking about 3D nanowires or other kind of materials. So if anybody wants to drop in, feel free. But I agree that's a big part of the problem. But that's a bit out of scope for the yield discussion. But it's definitely interesting.
Mhm.
But I think it's quite important to determine the light output we need, right, from the chips, in order to get to the brightness levels which OLED has. And I mean, to deliver on the energy efficiency promise of micro-LEDs, I think is an important battle we need to fight. But I mean, just looking at this cost equation, yeah, and if I take Barry's numbers, then we are basically looking at about $100, which we could afford for the front plane. Is that correct? I think your numbers added up to like $43, $45 for everything, but the light emitting part.
Yeah, about $100 is about what I said.
Okay.
If you're interested, I could send Ron a copy of the cost analysis that I've done, and he can share it with you if that would be of interest.
Mm-hmm.
Yeah, for sure. Yeah.
It would
Super great interest.
Yeah, I would share. What I've done is to look at OLEDs as they exist today and have a pretty good sense of all the costs today. And then I projected forward based on what I knew would happen in the industry in terms of cost reductions or in fact cost increases. And that's where I gave you the quotes, but I can give you more detail of that if you're interested.
Yeah, it would be super cool. And let me throw in some numbers from my side as well. So if we're looking at these $100, and I mean, I would assume that color conversion goes on top, but just like take this as a proxy now. And we have an 8-inch wafer which has 600 million chips. Yeah, then this would yield, assuming 100% yield, right, for the moment, it would yield 24 displays from that wafer. Which means that wafer could cost 2,400.
Should cost, yeah.
Yeah. I mean, from the epi side, this is easy. The epi cost is a fraction of that.
Mm-hmm.
And if we go to 300 millimeter, the equation gets better eventually. Yeah. So that to me sounds reasonable. And I mean, then we would be competing at cost with OLED, which seems really like a long stretch, but there's of course also the 100 yield assumption in my back of the envelope equation I just did.
I just want to add something. We should never lose sight of actually what the target is, because it's not just competing with OLEDs, because when Samsung started making micro-LED displays, they talked about 2,000 nits, so I think that's their goal was. But today, LG just announced this year their latest OLED TVs, and they reach over 2,000 nits for OLEDs. So for consumers to actually start buying micro-LED TVs, which are bound to have quite massive premium in price over OLEDs in the first years, you're going to have to give them something, beside the name micro-LED. And so it should be, I don't know, it could be better performance, but it has to be better performance. So it has to be some other unique advantages, because otherwise there's not really the point, right? Because in display performance, you're going to not get much improvement with micro-LEDs if you don't get, beyond just saying it's micro-LEDs. And I think that was, I mean, in the first years of OLEDs, we've seen this problem, right? When you went into a retail store and looked at, still today, when you look at LCD, the display quality is very, very good. So when you go and buy a TV, OLEDs may be better, but LCDs are very good. And with micro-LEDs, we seem to have an even lower kind of difference in terms of performance, especially visible performance with TVs. And I think that's going to be a big issue. So you should always consider, so the target is not just get to the same price level of OLEDs in the future, because what's the point, right?
Yeah. But so you think there is no margin to have premium for micro-LED televisions? You think it needs to be better and same cost, or lower?
No, it could be better, but it should be better in something you can actually realize. For example, if you have a tile TV, I can make the case that these tiles have a lot of advantages, right? So for example, if it's part of your TV breaks, maybe you can replace just one tile and not the entire TV, right? That's something consumer can understand. For example, we have the burn-in issue, right? With OLEDs, you have limited lifetime. LEDs are much better. That's an advantage. Maybe brightness, maybe efficiency, but you're going to have something, right? Otherwise, why pay the premium? I mean,
Well, I mean, the advantage that OLEDs had really was the contrast ratio at the beginning. Where OLEDs are challenged, even though they're now up to 2,000 nits, is going to be to meet the HDR requirements that could get to 4,000 or 10,000 nits. And it seems to me that since that's just a point solution, you know, where you have a few pixels up that high, that's where micro LEDs will have a great advantage. I don't think OLEDs will ever get that high.
yeah, maybe that's true.
And the other one is lifetime. Even though the efficiency may be equal or close, I think micro LEDs will always have a lifetime advantage, especially at the higher luminance levels.
That's right, and I think that's mostly important. Yeah, in some applications that's very important. We see this in IT displays, in automotive, and that's really, I think, the segment that micro LEDs should be or are targeting. But when we talk about TVs, I still have an OLED TV from 2016, I think, and I don't have any burn-in problem, and not many consumers are actually suffering from their OLED TVs. So we have to.
The problem was really more for monitors, where you kept the image the same. The TVs pretty much really never had a burn-in problem, unless people were arbitrary and showed a given image the majority of the time.
Yeah, and I think that's, again, we come back to maybe one conclusion that should be what kind of segments you're actually targeting. Like, if you're a micro LED maker, maybe you should go for automotive, for gaming monitors, for tablets. That's difficult. Maybe IT monitors, things that are, you're going to have clear advantages. Mobile devices, obviously.
In the early years, I think micro LEDs have a real advantage in terms of automobiles that neither LCDs or OLEDs can meet, and that's the wide temperature range. Yeah. And also the brightness question. So I think, I mean, I'm not in the particular market, but it seemed like that would be where the industry could get real advantage. And obviously with AR, which OLEDs will never get to the kind of 100,000 nits on a 1-inch display that they have to get to.
Yeah. Sure.
Yeah, but I think also now interesting to see there was a lot of public news on different pages about the companies are starting to approach watches with micro LEDs. I think there are now already 3 companies announcing this. So this is, I think, just a trial. It's early stage, and you just Alexander, you calculate, right? 600,000 micro LEDs for a watch, and you say 600 million, it's 1,000 watches, and then calculate the dollars of one wafer. So it's just $1 per watch. So I think this is in the range where it's, let's say, a good start. It's not really the display or the micro LED sizes are okay to handle, and but yeah, I think this is just the first approach and trial, and this was already until now many are LTPO, so it's already low power consuming OLEDs at the moment.
Yeah, I agree.
I think it's a good sign for micro LEDs, and that is, here's a company like Apple that's really willing to spend close to 5 or almost some believe it's really 7 or 8 times what the OLED is, and still go after a particular market, and with the expectation that they're going after they sell about 50 million smartphones, and they're talking about 10 million for the micro LED portion of it. So you can just about see what they're trying to do, which is get a foothold and then move up, just similar to the way they did OLEDs. So I think it's a good.
I would also add that I think Apple is, I mean, if you look at the last 10 years, they're always trying to control their supply chain and have their own technologies put into place. And I think one of the main advantages for MicroLED for Apple is the fact that they have much better control. So, you know, with OLEDs, they've been relying on a very limited number of suppliers for, you know, the watch or the iPhone. And suddenly they have this opportunity to actually, you know, use a much better supply chain for them and actually make some of the process in-house. And I think that's a big advantage. And I agree with Oliver. I think that's going to be more of a test case for Apple. It's going to be a very high-end kind of watch, a very, you know, premium kind of device. But we'll have to wait and see. We're here 2025 now. So
other companies are already announcing it for 2023 or 24. So, but the race is on, and that's also interesting that I think one day after the first announcement came, another company came, and now the third one came, and that exactly, if you go 12 years back to when OLED started, but it takes time, yes, and I think the more time it takes, or not more time it takes, but the process chain will get more, let's say, more clear, and the individual processes are more defined, and yeah.
I agree. I think one of the main things we should all understand, this is a long-term kind of, you know, technology or market. I remember hearing Barry talking, you know, years ago about how Apple is the axis of evil for the OLED industry. Apple and Sharp, it was in the day. And, you know, it took a lot of courage for Samsung to actually start making active axis OLEDs where the performance was not very good, the price was high. I mean, people were returning their smartphones saying, you know, something is wrong with them, the display is not good. But they understood where this is heading. And I think many companies now understand that MicroLED is, you know, that's where the technology is heading, maybe 10 years from now. And you know, that's the, you know, the time to jump in and start developing your own technology, you know, 10 years in advance. Yeah, anyway. So anyone else want to raise maybe another topic before we wrap up?
Maybe only a quick poll. Who is going to be at Display Week?
Yeah.
Okay, looking forward to see you guys there.
Yeah, and we hope we're actually working on a on-site meeting for the MicroLED Association. So it's going to be nice to see you all in person. Okay, so thank you all for coming and hearing the lecture today. Again, feel free to download the white paper, and see you on the next call.
Thank you.
Organizing.
Thank you very much.
Thank you, everybody. Bye-bye.